Welcome back to the channel. So as I was editing the last video, in that video, I was comparing an unknown coffee sample to 4 other samples, and I was making that comparison using Pearson correlation. And all of the samples were highly correlated with each other on the order of 9998 to 9993. And so I mentioned that we don't really want to rely on correlations that are that close for trying to sort out these samples, because when you're talking about the samples that are that highly correlated, that's probably on the order of the correlation of our actual replicates. Now, in this case, we can see that these only really differ in the 4th decimal place. And in the real world, this is a really tough call to make. So for instance, sample A, if I measured that 4 times and computed the mean correlation, it should be on that order of similarity with itself. Particularly if you have a high quality instrument, you have a pretty homogeneous sample, and there's no other artifacts that are sort of popping up. And in the next few videos, we're going to dig a little bit more into understanding our replicate analyses so that we can have a better intuition about perhaps which measurements were high quality, which were lower quality, and perhaps need to be removed from the study. And so this video will feel a little bit incomplete because we're not going to address the low quality measurements here, but I want to help you gain some intuition about what that means and a number of ways that we can use to first identify which of those measurements we might need to remove, or which of those samples we might need to remove from our study or re-measure. Let's get started. Now, in the replicate analysis, where we're focusing primarily on just understanding the correlation, I've assembled the data a little bit differently. I am merging my metadata with several NIR spectra. And so rather than aggregating on sample ID and computing a mean spectrum for each sample, we're now leaving those replicates separated. And so with this, we can gain a better intuition about how correlated those samples are. So what I want to demonstrate next is this chained method we're going to use to sort of gain some visual intuition about this. And then I want to show you how we can expand this to look across our entire data set. So first, I am selecting sample 1, so sample ID 1, and I'm just going to choose some narrow range in the NIR domain. So we're going to start around 1500 nanometers out to 2200 nanometers, transpose the data, and I'm just showing you what that data frame looks like here. So next, let us plot that data, and visually you can see that these data are pretty highly correlated, meaning that when one spectrum moves down, the others do too. When those points begin to move up, they all move together. And this is without any signal processing. So this is what the data just looks like. If you want a clearer view of what the data is, you could pass subplots into plot and set they equal to true. And we will get these vertical subplots. And again, you can see that based on the signal magnitude and the overall trends within the data, we are getting pretty highly consistent data. And so one thing, again, about chaining these methods, that we can pretty easily switch the method out. And so now let's look at the correlation amongst these samples. And we can see that these are correlated. If we look at the minimum correlation across each of these, we're looking at 0.9998. And so this, again, is what I was talking about when I was identifying this becoming an issue, is that these correlations are on the order of the correlations of a highly reproducible measurement. And so we do want a way to gain more confidence in the sorting by splitting these out in this case, but we can also leverage this idea for assessing measurement quality. So going back to that idea about measurement quality, I have this piece of code here where I am now going to create a list of sample IDs. And if I separate this out, we can run this cell and get my sample IDs. And here we're just getting all of our unique samples. And the idea is that we'll pass each of these index values into this for loop and compute the correlation, again, return the minimum, and then take the average of those minimal correlations and store that into this core data dictionary, and then convert that dictionary into a pandas series. So I'm going to run this and show the first 5 rows. And when we do this, you can see that we're getting some samples that are pretty highly correlated. If we continue a little bit more and show the first 10 rows, again, we're seeing correlations that are really, really high. So 0.999, 986. And so what I want to do next is look across the bottom 10, so the data that's the least correlated, and see what we have here. And so when it comes to the data that's least correlated, we actually have some samples that are actually negatively correlated, meaning as one spectrum moves up, the other point is moving down or in the opposite direction. And this would maybe posit that we have a bad measurement or at least a very heterogeneous sample. And we can see that even as we move across, these are the sample IDs, 57, 59, 26. We have data that's either anti-correlated or very weakly correlated. And this is how we can begin assessing measurement quality. So this is a key intuition and perhaps help us to design better studies or clean up our data by removing these samples that even based on the replicates are not highly reproducible in this case. And so next, let's dig into these samples so we can try to understand why this was the case. So we'll begin with the most extreme case, which was sample 57. And if we look here, if you look at sample 57, this is one of our over-the-counter pharmaceuticals. This is acetaminophen, and this tablet itself was red, white, and blue, and it was a rapid-release gel capsule. So this sample was actually a pill that I just placed on the sensor. So undoubtedly, this would perhaps look like a bad sample, and based on the data, this is the case. And so now let's look at the spectra behind this anti-correlated data. So I'm going to copy this down so we don't lose it. I'm going to set the loc, and let's look at all the rows. And then we're going to look at 1554 to 2202.0. And there you see it. Let's transpose that and let's plot the line plots. When we look at this, you can see that we are getting indeed a very poor measurement. So this purple trace looks like perhaps it's a better measurement. At least we have something that resembles a spectrum with peaks in it. And the blue, red, orange, and green all look pretty bad. And so this is why we're getting data that looks pretty anti-correlated, because you can see as purple moves up, the orange and blue are moving down. And even with some signal processing, we're not likely going to salvage the sample, perhaps suggesting that in our methodology, we should indeed rely on grinding the pills before measuring our sample. So let's move to 26. So 26 is a plastic container. It is polyethylene terephthalate, colorless. And let's look at that ID. It looks like we actually have just a bad measurement, just one where the probe wasn't fully contacting the surface. So I might treat this scenario differently, where it looks like by removing this lower brown trace, I would substantially improve the measurement, because some of this other data looks like it could be addressed with some signal processing like standard normal variate to improve the data. So let's get a couple more. Let's try 43. So we're kind of on the high end of our low end. And this is a plastic bag. It has two colors, white and blue. This is actually one of the bags that our frozen salmon came in. And so let's look at what that data appears to be. So this looks more like where the thickness of the bag may have varied a tiny bit. And there's ways that we probably can address this issue with some signal processing. For instance, let me show you what I mean by that. So if we take this data here, and before we transpose it, let's pipe our SNV method and then transpose and plot. You can see how we have significantly cleaned up the data. We've removed a lot of that scatter in the Y direction, but now we're getting to something where overall the data looks fine enough, especially compared to the earlier point. So let's try 24. Okay, 24 is another plastic container. This is a polyethylene terephthalate colorless, animal crackers. So I recall this container. When I was measuring this particular container, the bottom, I recall, was significantly thicker than the sides, and the sides also had some artwork. So I'm not surprised that we are seeing something that's sort of weakening our correlation across these replicates. Let's look at what the actual data looks like in this case. Let me remove this for now. And yes, okay. So again, this is what I've seen with some of the other containers around the thickness, where perhaps some of these points are from the bottom of the container where I'm getting more plastic at contacting the sensor. And I would not be surprised if this purple trace here and this blue trace around the sides where the container is a little bit thinner, or there's other artifacts interacting with this signal. And so I'm inclined to keep this here. This could be another case where some signal processing like this SNV could be beneficial. We have other techniques that we could use. So not only standard normal variate, but in previous videos, we've also applied Savitzky-Golay, where let's just try a window length of 3 and a polynomial order of 1. And then let's transpose this again. And you can see how we're already cleaning up that signal. And even we can try a larger window. And you can see how we're really bringing that data back together. So there are some cases where we have bad measurements like 57. And then there's other cases where we need to just process the replicates to get a more representative sample. And we will handle those cases differently. And overall, this will improve the quality of the data set. I hope this video was beneficial in helping you to build some intuition about what the data looks like. And in the next video, we're going to use a different technique for assessing our replicate data quality. In any case, I'll see you in the next one. Peace.